Good morning, IB Math. All right, moving on to 6M. Now we're going to focus on the double angle identities. And I want to kind of derive these for you a little bit so you can see how we came about them. First, we know that from the previous lessons, the sine of two angles is the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. But what about if we made the angles the same? What if we said the sine of A plus A? In other words, double angle. This is going to be 2A, isn't it? We're going to get a formula for the sine of 2A. Well, if I substitute it in, I'm going to get the sine of A, the cosine of A, plus the cosine of A, the sine of A, because the angles are the same. So I get sine A, cosine A, sine A. Are they the same? Yes, they are. I've got two of them. 2 sine A, cosine A, and here is our first double angle identity. Let's do the same thing for cosine. We know that the cosine of the sum of two angles, the cosine of A plus B, is the cosine A cosine B minus the sine A sine B. But now what if I let them be the same? Then I'm going to get the cosine of A plus A is going to be the cosine of A times the cosine of A minus sine A, sine A. So I've got my identity here. The cosine of 2A, oh dear, this should be A and A, sorry, make them the same. So A's and B's, so no A's and B's, just A's everywhere. So that's going to be cosine squared A minus sine squared A. Oh, now look at that. Is that an identity over there? Can I simplify that? Does that equal 1? No. If it was sine squared plus cosine squared, it would equal 1. But I can do some things with this. So for example, where I've got cosine squared, I know that that's the same thing as 1 minus sine squared. So I'm taking cosine squared and substituting in 1 minus sine squared. And then I have this minus sine squared. Combining like terms, I get 1 minus 2 sine squared A. And I have another identity for the double angle. So cosine of 2 times an angle could be cosine squared minus sine squared, or 1 minus 2 sine squareds. And I can make another one here. I could do the cosine squared A minus sine squared, I know is the same thing as 1 minus cosine squared. Simplifying this, I'm going to get cosine squared minus a negative cosine squared. So I'm going to get cosine squared, I'm going to get two of them, 2 cosine squared A's minus 1. And I have another identity. So cosine of double angle, cosine of 2A, has got 3 different possibilities for the double angle formulas there. And this is how we got them. Now what about tangent? Well, we know that the tangent of A plus B, the sum of the tangents was tangent A plus tangent B all over 1 minus tangent A tangent B. So let's do our substitution now. I think this is one of the exercises. I don't think the textbook gives you this one. I think it asks you to prove this one. The tangent of A plus A is going to be the tangent of A plus the tangent of A all over 1 minus tangent A tangent A. So this is really tangent 2A equals 2 tangent A's over 1 minus tangent squared A. And I could get fancy schmancy here, and I know I've got a substitution for tangent squared that I could plug in there, but I don't think I want to do that. All right, so here we have our double angle identities. Oh, let me circle that last one. We've got 1 for the sine of 2 times an angle. We've got 1, 2, 3 for the cosine of a double angle. And we've got 1 for the tangent of a double angle. All right, let's see how these are used. Let's do a couple of sample problems. See how they're used. In the first one, let's say I want to let's prove the identity. Prove that the sine of 2 times an angle divided by 1 plus the cosine of 2 times an angle is really the same thing as the tangent of the angle. So this is an identity we're trying to prove. And when we're trying to prove identities, we're always going to pick either the right hand or the left hand side and work on that, and to get it to look like the other one. Clearly, this is going to be a left-handed proof. I'm going to substitute in here. Well, the sine of 2 times an angle, I know that's the same thing as 2 sine cosine over 1 plus the cosine of the double angle. Now I've got a whole bunch of different possibilities that I can plug in here. I'm going to use the 2 cosine squared minus 1. And let's see if I simplify. I use this one because I know the 1s are going to cancel here. And in the top, what am I going to get? 2 sine A cosine A over 2 cosine squared A. Well, let's see. Can I cancel the 2's here? And I'm going to get sine A cosine A over cosine squared is really just the same thing as cosine times cosine. So I canceled 2 over 2 here. I'm going to cancel cosine over cosine there, and I get sine over cosine, which of course is indeed tangent. So here it is. Identity verified. All right. We can use these identities to solve equations, to verify, and if you see something like a tangent 4 or sine of 4 alpha, then I can just rewrite that as the sine of 2 alpha plus 2 alpha and break it up and then break each one of those up again. That gets a little bit confusing. Let's take a look at another type of sample problem that we can do with double angle identities. Suppose I tell you that I have an angle and that the sine of the angle of alpha is 4/5, and I'm going to tell you that it's an obtuse angle. The sine is obtuse, and let's see, the cosine of some other angle, beta, is 8/17, and this is an acute angle. So I've got 2 angles here. One angle alpha, the other angle beta, and the sine of angle is 4/5, and it's an obtuse angle. The cosine of beta is 8/17, and beta is an acute angle. And I want you to find, in exact values, the sine of alpha plus beta. All right, so the sine of alpha plus beta. The sine of alpha is 4/5. So what would be the cosine of alpha? Well, if I take a closer look here, it's an obtuse angle where sine is positive. This is going to be in the second quadrant. So think about this angle in the second quadrant. If you need to draw your unit circle, 4/5. What's the cosine of that angle going to be? What's the cosine of alpha? I'm going to need that in a minute for my substitution. The cosine, well, in the second quadrant, sine might be positive, but cosine is negative. Cosine is adjacent, so that's 4/5, 3/5, cosine 3/5. How about beta? Let's take a closer look at angle beta. Again, unit circle. Beta is 8/17, and it's acute. It's in this angle right here. It's in this quadrant right here. So the sine of beta is going to give me, let's see, opposite 8 over 17. Pythagorean theorem says that side is 15. So 15 over 17. Again, I'm just looking at the triangle. The fact that it's acute means it's in the first quadrant, positive. Obtuse means it's in the second quadrant, positive. So the cosine is going to be negative. All right, so now the sine of alpha plus beta is going to be, and if I write this down as my two angles, it's going to be sine alpha cosine beta plus cosine alpha sine beta. So the sine of alpha plus beta is going to be, I'm going to substitute all my numbers in here. So let's see. The sine of alpha was given as 4/5. The cosine of beta was given as 8/17 times the cosine of alpha. I calculated that to be negative 3/5, and the sine of beta I calculated that to be 15/17. So let's see, what am I getting here? 4 times 8, 16, 32. 7 times 5 is what's that? 85-ish. Plus. Minus a negative 45 over 85, negative 45 and 32, negative 13/85, the exact value. Oh gosh, there it is. All right, let's look at another problem here, a little bit more involved, solving, a little bit harder. I want to solve the equation 3 times the cosine of 2 theta minus the sine of theta equals negative 1. And I want to do it from 0 to 360 degrees. Whoops, parenthesis there. 0 and 360 are the same, so I'm going to use a parenthesis there. So degrees, I'm going to do it in degrees. I could have done it in radians, 0 to 2 pi, and just done my calculating in radian mode. Doesn't matter. The degrees, the angles are a little bit nicer here. First thing I notice is the cosine of 2 theta. I'm going to have to do a substitution here. Well, with cosine, there's lots of different possibilities. There's 3 different substitutions. Which one am I going to choose and why? Well, I notice I've got sine over here. I'm going to pick the substitution that deals with just sines. And that way I'm going to have a new equation with only sines in it. So cosine of 2 theta is the same thing as 1 minus 2 sine squared theta. All right, so let's clean this up. Distribute the 3. I'm going to move everything. I'm going to add that over. I'm going to add that over, subtract that over, get it in standard form, and I get 0 equals 6 sine squared theta plus sine theta. Subtract 3 from both sides. Minus 2. Does that seem right? All right. Now I want to see if what I can do with this. I notice that I've got a quadratic here. Can I think of 2 things? Let's see. Can I split the middle term on this? 6 times negative 2 is negative 12. Can I think of 2 things and multiply together to give me negative 12, add up to give me a positive 1? I think I can split the middle term on this. 6 sine squared theta plus 4 sine theta minus 3 sine theta minus 2. So I'm splitting that middle term. Group 6 sine squared theta plus 4 sine theta plus negative 3 sine theta minus 2. Out of this group I can factor, what does it look like? A 2 sine theta And what am I going to get left with? 3 sine theta plus 2. What can I factor out of this group? Well, not much. Can factor out a negative, and I'm left with 3 sine theta plus 2. They are the same, which means I can factor that out. And I get 3 sine theta plus 2 times 2 sine theta minus 1. Factored. Set each factor equal to 0. 3 sine theta plus 2 equals 0. And 2 sine theta minus 1 equals 0. Subtract 2. Divide by 3. The sine of theta equals negative 2/3. Add 1, divide by 2, or the sine of theta equals 1/2. Oh gosh, let's see. I'm not dealing with very nice. Well, the sine of 1/2, actually, that's the unit circle angle, isn't it? Negative 2/3. Can sine ever go down as low as negative 2/3? What is the range of sine? Sine goes, remember the sine wave goes from -1 to +1. So yes, it does go down to 2/3. In fact, it's going to go down there twice, isn't it? Same thing here, between 0 and 360 degrees. All right, so where is the sine equal to 1/2? Well, the sine of theta in the first quadrant, theta could equal 30 degrees, pi over 6. But where else? Sine is also positive in the second quadrant. What angle in the second quadrant has a sine of 1/2? 150 degrees. How about negative 2/3? Oh gosh, I don't know. That's not a nice, well-behaved unit circle. But I know that sine is negative in third and fourth quadrant. There's going to be 2 solutions in the third and fourth quadrant. I'm going to use my calculator here, and I'm going to do the inverse sine of negative 2/3, and I get negative 41.8 degrees. And what other angle? Negative 41.8 degrees, but sine is also negative in the fourth quadrant. So if I take 360 minus 41.8, I'm going to get 318.2. So there they are, the 4 solutions for solving it. One of them was nice, well-behaved unit circle. We should know that. The other one, clearly I needed a calculator. Couldn't do anything for that. All right, so I want you to go ahead and do assignment 6W. It's on page, where is it? Where's my notes? Page 408, numbers 1 through 7. Let's talk about them for a moment. Problem number 1, you're going to be proving some identities using double angle identities in there. Remember, things like this. What's the cotangent of 2 alpha? Well, cotangent of 2 alpha would be the same thing as 1 over the tangent of 2 alpha. Yes? And then I could substitute from that. So if you see that, or cosecant or secant, substitute in 1 over sine or 1 over cosine. If I have the sine of 4 alpha, well, isn't that just the same thing as the sine of 2 alpha plus 2 alpha? And I could break it up using that. And then I'm going to have sine of 2 alphas. I'm going to break up each of those. Let's see. I think that the rest of them are pretty straightforward. I just realized I did my example, the other example, in degrees, and problem number 7, they are all in radians. So I hope that doesn't give anybody a hard time. But go ahead and try these. Answers are in the back of the book with some of the work in some cases. But go ahead and see what you can do with these. Any you're not sure about, let me know, and I will post a solution. All right, guys. So time to get to work. Good luck. Talk to you again soon.